In this lecture, we will look at growth rate as a function of undercooling, delta T, which is the temperature at which the transformation is taking place minus the transformation temperature Tr. So, we will consider the two cases of interface controlled growth and diffusion controlled growth separately. So, in the case of interface controlled growth, as we had seen in the last lecture, the growth velocity V can be written as lambda nu e to power minus delta Gd divided by Kt multiplied by 1 minus e to power minus V delta Gv divided by Kt. So, let us see what happens if I reduce the temperature at which growth is taking place. This results in a larger undercooling, and a larger undercooling would result, as we had also seen in the previous lecture, that the volume free energy change would increase, and if the volume free energy change increases, then the term in the circular brackets 1 minus e to power minus V delta Gv divided by Kt would increase. So, this would have a contribution of increasing the growth velocity. However, we also have this term. If I look at reducing temperature, increasing undercooling, and we can, it is fair to assume that delta Gd is fairly constant, then increasing temperature in the denominator term here would result in this exponential term e to power minus delta Gd by Kt to go down. So, here also, as in the case of nucleation, we have two terms. With increasing undercooling, one term increases, the other term decreases. So, if I were to graphically illustrate this, that as increasing undercooling, this is the term e to power minus delta Gd divided by Kt reduces, while the second term 1 minus e to power minus V delta Gv divided by Kt, this curve increases. And as a result, combining both of these curves together, we get the growth velocity or the growth rate as a function of undercooling to initially increase and then starts to reduce with at some particular undercooling, calling it as delta peak, I get a maxima in the growth rate. So, just like nucleation, in the case of interface controlled growth, we also have a peak in the growth rate. Like nucleation also, we had a peak in the nucleation rate as we changed the undercooling. Let us also look at diffusion controlled growth. What happens in this case? In the case of diffusion control, in the last lecture, we had the growth rate written as V equals half C0 minus C alpha, the supersaturation, divided by square root of C beta minus C alpha times C beta minus C naught multiplied by square root of d upon t. So, let us look at what happens here. As the temperature of transformation is reduced, that means the undercooling is increased. This results in, let us say first let us look at supersaturation. If we look at the phase diagram, it would be very clear to you that C naught minus C alpha would increase. Let me quickly show this. This is C naught, the chosen alloy, and we are looking at growth rate at some particular temperature, and this is C alpha. Very clearly, as the temperature of transformation is reduced, C naught minus C alpha would clearly increase. What other term is affected as the temperature is changed or the undercooling is changed? The coefficient of diffusion. What is the coefficient of diffusion? D. We all know that D equals D naught e to power minus Q divided by RT, where Q is the activation energy for diffusion, T is the temperature, R is a gas constant, D naught is the frequency factor. And if temperature of transformation is reduced or the undercooling is increased, this would result into the diffusion coefficient reducing. It's fair to assume that Q and D naught are independent of temperature, and hence very clearly the exponential term e to power minus Q upon RT as temperature is reduced would decrease, because as the temperature is reduced, the mobility of atoms also go down. Here again we have two terms, one term increasing, the other term decreasing as the undercooling increases, and hence we get a very similar pattern of growth rate versus delta T, that is, it goes through a peak. So, what we have done, we have reviewed nucleation rate, we have reviewed growth and growth rate, reviewed briefly the mechanism of both nucleation and growth, and we have seen that in all cases, whether it is homogeneous nucleation or heterogeneous nucleation, the nucleation rate goes through a peak as the undercooling increases. In the case of growth also, whether it is interface controlled growth or diffusion controlled growth, the growth velocity also goes through a peak as the undercooling increases. So, at very small undercooling, both nucleation and growth rates would be very low. At very large undercoolings, again both of them will be low, and at intermediate undercoolings we will have a maximum in both nucleation and growth rate. Now, we would now combine these ideas of nucleation rate and growth rate to come up with the kinetics of the overall phase transformation. So, coming to the kinetics of overall phase transformation, we come to the well known kinetic theory called the Rami kinetics. This also have been dealt in great detail in part 1 of the course. So, Rami kinetics take both the growth rate and the nucleation rate, combine them together to come up with a very neat relationship between the fraction transformed as a function of time. Now, one can imagine several scenarios. For example, one can consider nucleation and growth taking place simultaneously. So, therefore, a situation like where alpha phase is transforming to the beta phase at t is equal to 0, we only have alpha. At some time t1 greater than 0, I have some nuclei formed and some of the older nuclei also have undergone growth. And as time progresses further, I will have different nuclei which have nucleated at different times, grown to different sizes, and fresh nucleation also taking place. So, this is one kind of scenario one can imagine, and in this we may have a constant growth rate, or we may have a parabolic growth rate, we may have a constant nucleation rate, or we could also have varying nucleation rate as well. Second scenario one can consider is at t equal to 0, we have the alpha phase, and within a very small fraction of time nucleation is complete. So, essentially at t equal to 0 itself, more or less, nucleation is complete. Now, this is a possibility in a situation where heterogeneous nucleation is taking place and there are limited nucleation sites for heterogeneous nucleation. So, those sites quickly get saturated. So, there is site saturation taking place, and then after that these nuclei, all the nuclei simultaneously grow, and this is a picture at some time t. This way one can build many different scenarios and they can be combined together into what is known as the Rami relationship. There are some assumptions involved in this Rami analysis. The key assumption is nucleation takes place randomly. So, random nucleation, the nuclei that are formed are spherical. So, we are saying there is 3D growth, but there are 2D growth possible, 1D growth also possible, and alpha is transforming to beta in the form of precipitates. So, the Rami relationship, the Rami analysis shows that at time t, the fraction of beta transformed is given by 1 minus exponential minus V beta E divided by V, where V beta E is termed as the extended volume. For a review of this, you can go back to my lectures in the part 1 of this course, in which each of these terms and the extended volume in particular is dealt in detail. And V is the total volume. Then it was also shown that the extended volume V beta superscript E can be written as 4 pi by 3 times the total volume times integral 0 to t. So, V beta E is the extended volume at time t, the extended volume of beta. So, which is equal to 4 pi by 3 times the total volume and an integral term which integrates from 0 to t, the nucleation rate I multiplied by the size of the beta precipitate that is formed, r tau, which means the size of the beta precipitate formed at time t is equal to tau. So, RT cube, that is coming from the volume of the particle, times d tau. So, you are integrating all the nuclei that are formed throughout continuously as the transformation is progressing. So, tau is varying from 0 to the instant of time t. Now, with just these two expressions, we had dealt several situations. For instance, case 1 of the Rami analysis, which is the simplest case, where we consider that I is a constant, the nucleation rate is a constant throughout the transformation, and the growth rate or the growth velocity V is also a constant throughout the transformation. In this particular case, V beta extended, the extended volume becomes pi by 3 times V times the nucleation rate times cube of the growth velocity small v multiplied by t to power 4. If we take this, plug this into the into this expression f beta and compute what would be f beta, then f beta simply turns out to be 1 minus exponential of minus pi by 3 I times v cube times t to power 4, where pi by 3 I and v cube, as you can see, these are constants and they can be lumped in one single constant k, and hence f beta, the fraction of beta transformed at time t, is given by 1 minus exponential minus k t to power 4. This is a case where nucleation and growth are a constant. A second case, case 2, suppose we have constant nucleation rate while the growth rate is parabolic. So, we have parabolic growth rate. In this case, fraction of beta transformed as a function of time is given by 1 minus exponential minus k t to power 5 by 2, or simply I can write this as t to power 2.5. where K is equal to 8 pi by 15 times the constant nucleation rate times a constant, a growth constant B, and this growth constant B is coming from diffusion controlled growth, which includes terms like supersaturation, diffusion coefficient, etc. A third case is a situation which we discussed here, that site saturation has taken place and essentially at time t is equal to 0 all nucleation is complete. So, I will call this as a case where site saturation has occurred and let us say along with this the growth rate is parabolic. In this situation, the Rami relation becomes f beta equals 1 minus exponential minus k t to power 3, where k would be different from the constitution of k would be different from what we saw in case 1 and case 2. Now, I am sorry, this expression is not for parabolic growth rate, but this is for constant growth rate. The last case, case 4, we have site saturation and we have parabolic growth rate. Here, the Rami relation becomes 1 minus exponential minus k t to power 1.5. So, in all the 4 cases, case 1, case 2, case 3, case 4, as you can see, the time exponent is different. So, looking at this, and there can be various other combinations that one can analyze, and hence we can write the general form of the Rami kinetics. And the general form of the Rami kinetics is written very simply as f, the fraction transformed from the parent to the product phase, f is equal to 1 minus exponential minus k t to power n, where n and k are some constants which are governed by what kind of mechanisms are involved in nucleation and growth. Now, all of this so far what we have done have been dealt in great detail. These cases have also been done in great detail in part 1 of this course, and if you wish to review all this material, then you can go to the site which gives you the lectures for part 1 of the course, and for nucleation, discussion on nucleation kinetics, look at lectures, in fact not just nucleation but nucleation as well as growth kinetics. Look at lectures under week 5 and 6, part 1 of the course, for a discussion on Rami kinetics. look at lectures under week 7 of the part 1 of the heat treatment and surface hardening of this course. Now, what I intend to do, and this would be the subject of the next lecture, we will look at this Rami equation in some detail. First, purely as a mathematical function, how this function varies, how f varies as a function of time, what effect does the parameter n and k have on the function, and we will also look at the various, we will also look at the overall what kind of a transformation characteristics we expect, because as you know that both nucleation and growth vary or may vary as a function of time. So, overall how this function varies with time, we will have a look at this. Very briefly, if you will notice, when time t is equal to 0, the friction transformed as expected has to be 0. And when does 100% transformation take place? Well, that only takes place as time t tends to infinity, then f tends to 1, the friction, complete 100% transformation from alpha to the beta phase. So, we will see how the friction approaches 1 as time progresses, and then using the Rami kinetics, we will come to the important topic of time, temperature, transformation diagram, and then following that we will come to continuous cooling transformation diagram. We will stop here.